All right, so I'll go over this problem from the homework, problem number 4, and you're given a linear transformation from polynomials of degree 2 to polynomials of degree 2. That's what P3 means, polynomials of degree 2. And you're given the transformation acting on 3 polynomials. You're given the transformation as it applies to minus 2x squared, and you get another polynomial of degree 2. There's no constant term, but it's still of degree 2. You have t of this linear polynomial, 0.5x plus 5, and that gives me another polynomial of degree 2. And we have t of this polynomial, 5x squared minus 1. That gives me a polynomial of degree 1, which is also within the polynomials of degree 2 because it has degree less than 2. And we need to find t of 1, t of x squared, and t of ax squared plus bx plus c. Now you can find these one by one, but I want to show you a systematic way of cutting to the chase and actually doing the last one. If I know the last one, I can easily find these 3. Why? Because if I know the last one, if I set a equals 1, b equals 0, c equals 0, that's t of x squared, and that will give me this answer. Similarly, if I set a equals 0, b equals 1, c equals 0, that's going to give me t of x, which gives me the second one. And a equals 0, b equals 0, c equals 1 gives me the first one. All right, so as I said, I'm going to cut right to the chase and find this answer here. All right, so what we want to do is express these polynomials 1, x, and x squared in terms of the polynomials that we know the action of t on. We know what t does to minus 2x squared. We know what t does to 0.5x plus 5. We know what t does to 5x squared minus 1. So if I can express 1 in terms of these 3 polynomials, then I can find t of 1 in terms of these 3 expressions. All right, so that's the strategy. So in order to express 1 in terms of these 3 polynomials, I have to find constants d, e, and f such that d times the first polynomial, which is minus 2x squared, plus e times the second polynomial, which is 0.5 plus 5, plus f times the third polynomial is equal to 1. Right? This 1 is the polynomial I want to find, and I can consider that as 0x squared plus 0x plus 1. Now remember, I've talked about how you can consider polynomials as column vectors. This polynomial 0x squared plus 0x plus 1, you can simply consider that in column vector form. That's the same as the column vector 1, 0, 0. I've talked about how when you do polynomials in column vector form, it's better to put the constant term first. So this polynomial 0x squared plus 0x plus 1, that can be represented as 1, 0, 0. Okay. Now, let's match up this equation here. We have x squared terms, we have x terms, and we have constant terms. If you look at the x squared terms on the left-hand side, you get minus 2dx squared plus 5fx squared on the left-hand side, and you don't have any x squared term here, so you get 0. The x terms here have 0.5x on this side, 0x on this side. 5e minus f is the constant term here, and 1 is the constant term here. Now I did a little change here in making this go to the matrix. If I set this system of equations up as a matrix, I'm actually putting this last equation first here. This second equation is the middle equation, and this last equation is the first equation. The reason I did that was I want to put the constant term first, then the x term, then the x squared term. So this system of equations to find d, e, and f can be written in matrix form. Similarly, if we want to express x as a linear combination of this, this, and this, we set up a similar system. You can read through this at your leisure, but you get this system of equations, which in matrix form expresses like this. Okay. For x squared, we do the same thing. We get another system of equations. All 3 of them use the same matrix. I don't know why I did that, but let's try this. Okay. All 3 of them use the same matrix. Oh, I'm sorry, I went to the wrong page. Let's go back here. All right. Let's get back on track. All three of them, this one, this one, this one, use the same matrix. So in order to find all my unknowns, D, E, F, G, H, I, J, K, L, I can write this as this same matrix, and I do these columns one by one, and I get the result columns one by one. So this tells me how to get my matrix of unknowns simply by taking the inverse of this matrix. Okay, now so far I got in class. At this point I didn't follow up correctly, so now I'm going to follow up correctly. All right, now let's get back to the original problem. The original problem was to find t of 1, t of x, and t of x squared. All right, now I know that the polynomial 1 is a linear combination of these three polynomials, and the coefficients are d, e, and f. So t of 1 is t of d times this polynomial plus e times this polynomial plus f times this polynomial. All right, now using the linearity property, I can take these constants d, e, and f out. And I have t of this linear combination is the same linear combination of the individual t's. All right, but I know what t of minus 2x squared is. I know what t of 0.5x plus 5 is. I know what t of 5x squared minus 1 is. That was given in the original problem statement up here, right? Those were the givens for my t's. All right. So I'm in good shape. I know how to find d, e, and f. I know what these values are. So let me just summarize this, that the result of this t of minus 2x squared is this polynomial that was given to me. T of 0.5x plus 5 is minus 2x squared plus 4x minus 1. That was given. This t was also given. Let me express these polynomials in column format. Okay, now this has 0 constant term, minus 3x term, minus 2x squared term. So I write this as 0, minus 3, 2. Here I have minus 1. Sorry, this was wrong. This is minus 1, 4, and minus 2. So let me fix that. All right, so I need to fix this as a minus 1 here. Oops, it's not showing. There we go, minus 1. All right, and then this one here is f of 2x plus f times 2x plus 4. So that's 4, 2, and 0. Okay, so again, these are the vector forms of these polynomials. All right, so I have t of 1 in terms of these constants d, e, and f. In fact, t of 1 is a linear combination of these three vectors. And these three vectors, again, are the vector form of these polynomials. All right, so let's put this together as a matrix vector equation. A linear combination of vectors can be rewritten as a matrix times the vector of constants. And again, this is a minus 1 here. All right. Now, if I try to do the same thing for t of x, instead of def, I have the ghi, and that's the only difference between the two. All right, so I get the same matrix multiplied this time by the vector ghi. Same with tx squared. All right, so this is also minus 1. All right, so what does that tell me? If I put t of 1, t of x, and t of x squared together as column vectors, t of 1 is going to be this result. T of x is going to be this result. Hope you can see that. T of 1 was this result. T of x is this result, and t of x squared is this result. If I put them together as three columns, I'm going to get a matrix times a matrix, and each column of the result is going to give me. This one's going to give me t of 1. This one's going to give me t of x. This one's going to give me t of x squared. All right. Last step. What is d, e, f, g, h, i, j, k, l? Well, that's what I got up here. It's the inverse of this matrix. Just plug it in, and there we have it. If it doesn't flake out on me, there we have it. This is a minus again. That should be a minus. This should be a minus. And this gives me, as I said, this is going to give me, the first column is going to be 1. One is going to be t of x, and the next one's going to be t of x squared. Now, suppose I want to get t of c plus bx plus ax squared. Well, when I say t of c, that's the same as t of c times 1. Right? So in fact, I'm taking a linear combination of these vectors that I obtained from this. So this is going to be equal to, the first column is going to be 1, next one is going to be t of x, next one is going to be t of x squared. All right? And here I'm just taking a linear combination. So I get 1 t of x squared times cba. I just plug in my expression here, this expression for this matrix, and this is my final result. I'll get a final result in vector form. I need to convert back to polynomial form. So see if you can fill in the details, and that's the end of my video.